Globally, in our modern world, our better understanding of the impact of traditional working methods across different industries on the environment, society, and the world economy clearly demonstrates that we cannot continue as we have in the past. Since the start of the new millennium, we have endured one of the worst economic crises the world has ever seen, declared an environmental emergency, and suffered from the most devastating pandemic in recent times. These three events alone have caused us to rethink and re-evaluate how we live and operate. Where some industries have been left crippled and on the brink of extinction, others have thrived and adapted to new ways of working by harnessing modern technologies. Doing more with less is a common theme found in both the manufacturing and construction industries, but how is this happening and what knowledge and lessons are being learned and shared between the two industries? In this webinar, we shall explore these three questions. How are manufacturing processes changing the construction industry? What new technologies are being adopted? And what are the benefits and how do they combat the challenges we face? The global financial crash in 2007 was the most devastating of economic shocks since the Wall Street crash of 1929. It caused a severe recession here in the UK and many other major countries. In the years leading up to 2007, we were experiencing a period of economic growth with low inflation and dropping interest rates. These factors encouraged investors to typically look for more investments to earn more money, leading to a scenario of excessive risk-taking. The trigger was the US house pricing bubble bursting. A fall in house prices coupled with mortgage borrowers not being able to afford the interest on their payments led to global institutions that had borrowed and invested heavily were now left with huge losses. In 2008, here in the UK, this prompted a series of bank failures, even causing the bankruptcy of particular lenders. This caused a blanket disruption to most industries, including the construction industry. With organisation losses due to construction projects not progressing and a lack of work to bid for, redundancies became inevitable and workforces receded. This led to a need for change and smarter ways of working inside of the construction industry. A global climate emergency declaration was made in December of 2016. By making such a declaration, this is action taken by governments and scientists in acknowledgement that humanity is in a climate emergency. A government, by declaring a climate emergency, is admitting and accepting climate change, otherwise known as global warming, exists and that the control measures to date are no longer enough. These decisions stress that governments need to implement new, more extreme measures to reduce human-caused climate change. Due to new legislation, industries such as manufacturing and construction need to implement wholesale changes to combat climate change and adhere to regional and international laws. We are also dealing with the reality that there are fewer natural resources left. We know our natural resources are diminishing and that our built environment plays a role in this. A stunning 40% of global energy is used by our built environment. Buildings alone consume 25% of our water. Finally, building construction produces 30% of all global waste. In autumn 2019, the fragility of humanity was painfully exposed as COVID-19 began to soar across the globe. The mortality rate has been sobering, and the social and economic impacts have been devastating. Unlike the financial crisis of 2008, however, the economic impact of COVID-19 has targeted particular industries like hospitality and tourism, whereas certain industries such as online retail has thrived. A lot of this is being able to collaborate and operate remotely, technology being a key factor in their success. It must be possible to build good homes to people with ordinary jobs. These are the words of the late Ingvar Kamprad, founder of flat-pack furniture and product design giant IKEA. In 1996, Ingvar Kamprad had an idea that it must be possible to build good quality homes for the average income household. He came up with this idea when visiting a housing fair, and having become disillusioned and upset by all the housing he saw being exclusive and for the wealthy, his reaction was to make it possible to give the masses access to quality housing. He began this journey by contacting Swedish billionaire Melker Schörling, CEO of project development and construction group Skanska. It was obvious that their ideologies were aligned, and so forth came the birth of a new company, Boklok. As previously mentioned, Boklok was a joint venture between IKEA and Skanska established in 1996. It is considered to be a project development company. It is a company in its own right and doesn't sit under either the umbrella of IKEA or Skanska. Boklok has its own dedicated manufacturing facility and control over its site installation capabilities, therefore is considered a one-stop shop for the design, manufacture and installation of the building structure. Boklok currently manufactures and constructs approximately in excess of 1,000 homes a year and around 12,000 homes since 1996. Boklok homes are predominantly manufactured and constructed in Sweden, but have expanded into Norway, Finland, and construction is soon to begin here in the United Kingdom. In contrast to most housing development schemes or projects, Boklok has taken a more familiar approach to that found in the product design sector to methodologies apparent in the construction industry. Boklok's development can be summarised in three main steps or phases. Step 1. Investigation about the target segment. They delve deep into market analysis, acquiring metrics and information about what their customers' end-user experience was going to look and feel like. Step 2. Product development. This is fairly self-explanatory and looks at aspects such as prototyping and optioneering. This step could begin once they were armed with the knowledge and intel acquired in the initial phase. And finally, step 3. Establishment of the production system and supply chain. This would include aspects such as construction and manufacturing methodologies and material sourcing. This resulted in Boklok subsequently building their production plant once they knew what they wanted to achieve, as opposed to traditionally where a company would be set up, a factory is built, and then they are restricted by the confines of the structure instead of having something that is perfectly tailor-made to suit the organisational needs. Let's now take a brief look at the Boklok's product strategy. Product development based on customer insights. I think we've assessed this point enough, however, its importance is worth highlighting again. One of the key points in the strategy was to have a narrow range of products. This was achieved by creating standardised departments that have then been broken down into modules. By using these consistently scoped modules, the configuration of building structures and housing developments becomes standardised. The only variations include number of apartments, which are a cluster of modules per building. If we revisit the first point for a moment, does the notion of basing a construction project on end-user operations remind you of anything we've seen in the construction industry, particularly in the last decade? Building Information Modelling, or BIM, identifies the need for projects to look at an asset's entire life cycle instead of merely focusing on the constructability. We'll come on to this point later on in more detail. To summarise Boklok's approach to modular construction, we're going to look at the benefits they gained by using factory-based production. By having a narrow range of products, optimised production becomes more achievable. By using a factory-based approach, production becomes more logical and streamlined. Optimised production allowed Boklok to have a further optimised workflow. As production followed mass output to the same refined range of products, standardised and repeat processes could be achieved, enhancing efficiency. Recurring activities for repeat business allows project delivery time to be slashed sevenfold. Recurring activities allow the introduction of automated plant and machinery, resulting in a smaller workforce. In a controlled environment, continuous improvements and minor tweaks can be performed to further enhance production benefits. And finally, minimising waste as optimised workflows and processes make the most out of inputted materials. Also, having a manageable, select number of products restricts material variations, also contributing to less waste. By using modular techniques, Beauclerk claim 85% of the construction is performed in a controlled factory setting, resulting in a quicker produced, higher quality end product. That means a mere 15% of work is carried out in situ or installing the prefabricated modules on site. We hear the term building information modelling or BIM a lot in the construction industry. There are various schools of thought on what the term means and who it is applicable to, depending on what part of the supply chain you speak to. For the purposes of this webinar, we're going to summarise BIM as a structured data model fulfilling the requirements of an asset throughout its full life cycle. This aspect, I believe, is a key principle that has been happening in the manufacturing industry since it began. Products, theoretically, have always been manufactured to fulfill a particular need. They may vary in quality and cost depending on design and materials used, but generally speaking, that is the outcome, to make a product specifically for a desired purpose or purposes. I don't feel this has always been the case in the construction industry, particularly pre-BIM, as designs have traditionally been to suit constructability, focusing heavily on the capital expenditure or CapEx phase of a project. As the industry matures and clients implement smarter asset management systems by harnessing advanced technology, we're beginning to realise that the construction of an asset is a small proportion of an asset's expenditure for the duration of its lifespan. An example I'm going to use is when a consumer is buying a car, used or new. They will most likely take into account various factors, including the vehicle's upfront cost, in other words, what did the consumer pay for the car? The value of components and replaceable parts such as tyres and headlight bulbs. How much does the vehicle cost to tax each year? What is the miles per gallon of the vehicle, and subsequently, how much are the fuel costs likely to be? Are the seats comfortable? Is the vehicle spacious enough to suit the individual family requirements, and so on? If we now take a look at these factors in relation to our capital expenditure versus operational expenditure chart, only a single factor sits inside the CapEx from a consumer perspective, and that is the upfront cost or purchase price of the vehicle. All the other factors are relating to the operation of the product up until the car becomes scrapped, which is the longest span during the vehicle's life cycle. This means that the main expenditure will usually be during the vehicle's operation and maintenance phase as opposed to the purchase price. For a construction asset, we can take the same mindset approach as we did with the consumer product by using the principles of BIM. By keeping the end user in mind, projects can stay focused on end user needs and requirements. If we take a look at a building example, we will see the similarities to that of a consumer product. What is the capital expenditure? This will include, but not limited to, initial scoping and due diligence fees, planning and surveying, conceptual design and optioneering, detailed design, construction and fabrication, and as-built details and snagging. We can then take a more detailed look at whole life costings such as energy consumption, the lifespan and frequency of replaceable parts, the costing of subsequent expansion, the cost of future refurbishment and repairs. By using smarter technology, we can forecast performance and extract analytics relating to aspects such as thermal properties, structural performance, vehicle and personnel traffic, and so on. By doing this, we are planning for what the end user experiences are going to look like and ensure the asset is going to be fit for purpose, just like you would with a consumer product. By looking at an asset throughout its full life cycle, we can be constantly monitoring environmental aspects such as embodied carbon and emissions, from forecasting from the conceptual design stage to live analytics taken from the operation and maintenance of the asset. All these items allow us to make educated decisions later on if we were to either alter or repurpose the asset, and if we were to carry out a subsequent similar type project. This enables us to perform design tweaks that can be made by using the data we have gathered to refine decisions and make the asset more cost effective and environmentally friendly in the future. It is positive that the construction industry is moving in the right direction. However, there are various factors, or excuses if you will, as to why it is playing catch up. For a construction project to host that much data in a usable, operable fashion, both hardware and software requirements needed to be advanced. Arguably, this simply wasn't there 10, 15, 20 years ago. We can all remember the instability of producing two-dimensional deliverables in that time period, let alone producing data-rich three-dimensional models. The construction industry isn't solely in a controlled environment as per manufacturing. We previously discussed the benefits of prefabrication and modular construction. However, these aren't always possible due to certain site constraints, such as the relationship between the proposed structure and the existing conditions, where materials need to be used in situ. The numbers of and various types of stakeholders can have an adverse effect as to why progression has been slow in comparison to the manufacturing sector. This includes various sources of fluctuating funding due to working in both the public or private sectors, planning and regulatory bodies requiring certain specifications, making innovation more difficult but not impossible, and so on. When creating a consumer product, repeat tasks and processes can be achieved in a controlled factory environment. This is not the case with the majority of construction projects due to no site being the same and having other variables such as weather. In the manufacturing industry, it has always been more common to find readily available information such as assembly manuals, health and safety information and conformances, product care and maintenance information, data about materials, and so on. With building information modelling, we are now seeing this type of data become more readily available in the design, construction and operation of an asset. Not only are we hosting and adopting a similar process or methodology, we are also using the information from manufactured products in construction design and asset management. BIM object libraries are becoming more frequent, with manufacturing companies both showcasing their products and including all the relevant data about the item. This allows construction projects to essentially drag and drop manufacturers' components into three-dimensional models, increasing efficiency, accuracy, visual quality, and data availability. Visualizations have been used in manufacturing to advertise, market, and give consumers a reasonable sense of expectation. Although we've been seeing this kind of approach in architecture for years, whether it has been a physical cardboard model or rendered CAD output, we are now seeing visualizations as a more common output across the construction industry. The reason behind the use of visualizations is very similar as to why you would use them in product design or manufacturing, to help showcase the final asset and help manage stakeholder expectations, whether this be the end user or client, planning and regulatory bodies, construction site teams, and design teams. In a warehouse located inside the Dutch canal city of Amsterdam, between March 2017 and September 2018, the world's first single-span 3D printed bridge was steadily created using automated robotic arms. The project was a collaboration between pioneering Dutch 3D printing company MX3D, along with various industrial and academic contributors. The prospective site for this magnificent example of modern engineering and construction manufacturing is the Autodesk Achterbergwal Canal in Amsterdam. On the back of having completed the MX 3D bridge, it was unveiled at the Dutch Design Week 2018. Not only was the bridge a pioneering feat of where the construction industry is heading, it is considered a living laboratory. This is because the bridge is full of instrumentation and sensors monitoring all the traffic that uses the bridge, including walkers, cyclists and runners. All this activity will subsequently generate data about the structure's behaviour. The sensor network installed on the bridge was a collaboration between Autodesk, Force Technology, Lenovo and HBM. The purpose of adding a sensor network to the bridge was to create and develop a digital twin of the bridge to collect and live analyse the data. This collaboration between engineering, manufacturing and academics will provide an insight into the future potential of how living infrastructure objects engage and interact with humans and vehicles, and will become a key piece of the puzzle when moving towards smart urbanisation. We've talked about the adoption of technology, but we haven't yet delved into too much detail about the crossover of software tools. As building information modelling principles become more widely used, we're seeing the implementation of various software tools. This includes those that have been traditionally used in product design or manufacturing, now being used in construction. Autodesk Inventor CAD software provides professional-grade 3D mechanical design, documentation, and product simulation tools. It enables users to work efficiently with a powerful blend of parametric, direct, freeform, and rule-based design capabilities. With new workflows required by the Autodesk AEC collection, Inventor is becoming more adopted in the construction industry. Let's take a look at some typical examples of where Autodesk software crossovers could be utilised inside of construction projects. Autodesk InfraWorks is an application typically used for designing infrastructure type projects and for enhancing the visual surroundings of buildings projects. In contrast to other Autodesk tools, InfraWorks is 100% three-dimensional modelling. One of its core strengths is its parametric functionality and the object's relationship with the surrounding terrain. Generic bridge objects are parametric components that can be positioned at any station or offset along the bridge. They are created using Inventor and then utilised in InfraWorks via the Generic Objects library. Generic bridge objects are attached to the bridge and can be positioned numerically for accuracy. The generic objects have many applications. Not only can they be used to model unique specialised parametric bridge parts to attach to the bridge, but also to form the actual structure itself, such as creating arch structures or cable-stayed bridges, and even non-bridge related items such as construction equipment. In the construction industry, custom fabricators will want to provide additional value to all stakeholders by utilising building information modelling and Autodesk Inventor. Autodesk have improved the interoperability between Revit and Inventor by maintaining an associative link to the inserted Revit data. As users work on the models, the Revit projects can be accessed from a local file or coordinated via the cloud using Autodesk BIM 360 Common Data Environment. On referencing a Revit file, custom views from the Revit project can be selected in Inventor, allowing it to filter the coordinated model to just the information a user would need. Inside the Inventor browser, the Revit model is organised by category, allowing it to further examine the structure of the model and filter the reference model to the user requirements. Once placed into a user's Inventor assembly, the Revit model can be used as a reference model to help guide a team's design. Working with the native Revit project helps teams to locate their design using shared coordinates, size a design appropriately, and coordinate designs against the integrated reference model. Changes during the design process are inevitable. When the Revit model changes, designers will need to update the Inventor model to suit. As the Revit model is referenced into the Inventor assembly without file translation, any changes to the Revit project will also update inside the Inventor assembly. A change to a design and Inventor is a change everywhere the design has been referenced, automatically updating all downstream uses of a designer's model, helping to coordinate the work and keep up with change. When the design is ready, this can be outputted from Inventor as a 3D object ready to submit, closing the loop on the design cycle. Autodesk Inventor extends any CAD functionality to help manufacturers in the construction industry collaborate and coordinate on BIM projects. Forge is Autodesk's cloud development platform. The Forge platform is a set of web service APIs that you can use to build innovative cloud-powered applications. Forge APIs help you tap into your design and engineering data, which means you can streamline and innovate how you work. Whether you want to build solutions that automate processes, connect teams and workflows, or visualize your data, the Forge platform can help you do that and so much more. Today, companies are using Forge to build digital twins, visualize and analyze data, render photographs to 3D, integrate augmented reality and virtual reality, create product catalogs and configurators, automate design processes, and integrate SaaS products. Forge empowers developers and innovators from concept to completion. People across industries and companies of all sizes use Forge to unlock their data, improve collaboration, and build new services to address today's connected customer. I think we can safely say a lot can be learned from interdisciplinary or cross-sector collaboration and knowledge sharing. The main driving force and enabler has to be continuous technological advancements coupled with flexible adaptation. If the construction industry is to help tackle environmental, economic and social challenges, other industries such as manufacturing are a wealth of support and knowledge, adding fuel to the engine of progression. Fears that technology will usurp human-powered jobs should be seen as technology removing the mundane from activities and repetitive tasks, allowing more human resource and focus on smarter design and progressive thinking. We've seen the manufacturing industry adapt to change, with technology such as robotics working in harmony alongside human beings, interacting and outputting products more efficiently than people power alone could manage. But even manufacturing can't stand still, and doesn't, with increasing consumer demands, expectations, and countries around the world attempting to become carbon neutral. Importantly, do we have the choice to not change, with the ramping up demand of buildings and infrastructure across the globe, decreasing project duration time with less materials and less of a negative impact to this fragile planet we call Earth?